In the name of our Lord, we start with Poynting Theorem. A Poynting Theorem, for its understanding, we need a few things. One of those things is product rule from vector calculus. A product rule from vector calculus which states that del dot A cross B is equal to del dot A cross B is equal to B dot del cross A minus A dot del cross B. So this is that product rule we will be using. Very important thing for us. Now, I have actually derived this in one of our videos, that is electrodynamics 2, in previous video rather. Those students who are not familiar with it, they can go to that first and then come back. Second that I will need will be charge conservation and continuity equation. Charge conservation and continuity equation. Conservation laws are extremely important in study of nature. The basic purpose that they serve is they allow certain processes and prohibit certain processes. That means only those things happen in this world which obey those conservation laws. There are 7 absolute conservation laws, and then those processes do not happen at all which violate them. One of the conservation laws is charge conservation. Now there are 2 aspects in which one can look at charge conservation law. For example, thinking of the whole universe. Suppose this is whole universe. Okay, and this universe has charged particles, electric charge within it. And that electric charge, the total is, say, suppose that is Q. There's a total charge in the universe. This total charge can be 0, because then there can be as many positive charges as negative charges of equal magnitude. Then it will be 0, or it may not be 0. We are not sure about the total charge of our universe. Anyhow, suppose total charge is Q, and law of conservation of charge tells us that with time this Q will remain constant. It will not change. Q is constant. Q is constant. Okay. Now, this is one way you can look at law of conservation of charge. This is called global view. Global view. Global means, where we use the word global, global means large, big. When we consider the whole universe, we say it is a law that refers to the biggest possible entity, that is the universe. Such a conservation law is called global view. Global conservation law, or it's simply global view of that conservation law. We will understand it better with an example coming ahead. Another way of looking at it is you just consider a small volume inside this universe. This is a small volume inside the universe, and there in this volume, let me, in order to facilitate clear this view, let me enlarge it, magnify it, so that things are quite visible. But think this is just a volume out of the universe or within the universe. Now, this volume contains, say, suppose, total charge Q. Okay, and there is no restriction on this, in the sense that this Q must be constant. Not necessary. Q can change now. And if Q changes, suppose charge here, that changes. Suppose this charge decreases. Where does the charge go? If initially the charge there is 100 microcoulomb and this has decreased to 80 microcoulomb, where has the 20 microcoulomb charge gone? Yes, that must have flown across its surface, across this surface into rest of the universe. Into, you can see, across this surface. The good, that is called right, because it has, if it has to decrease, it must have crossed the surface. The surface is imaginary surface, hypothetical surface that you can think of around any volume. So this is these arrows show moment of charge across the surface. This is like electric flux. Instead of electric field passing through the surface, we now have charge passing through the surface. Now, the rate at which this charge will decrease, of course, the charge will decrease here. It will decrease. Its rate of decrease is minus dq by dt. Rate of decrease of charge is this. And this is directly proportional to, not directly proportional, this must be equal to the current through the surface. Current through the surface. That is current through the surface. Through surface. Now what is this? What is the current through the surface? But current through the surface can be related to current density J by this expression. J is current density is current by area through which it passes. Let us take these small infinitesimal things. Dis by dA perpendicular. What does this mean? Why? But this is okay if we write current density is current per unit area. That is okay. But maybe this perpendicular may actually, it may irritate some of you. Why do we write it like that? Because suppose you have a certain area oriented like this. It is orientation of an area is shown by, it is normal. Let it be orientation of this area. And current density is directed this way, horizontal, and this is inclined. Now this is current density J. This is the orientation of the surface. Area is a vector, because like this directed line segment, a directed area element is also a vector. But of course, with a difference, it is called a bivector. Mathematicians do not stop in imagining things. They can then think of volume as a vector, then higher dimensional vectors, and so on. Now, we can, since not all current density will be counted as flux, because it does not, all of the J is not flowing perpendicular to this area or parallel to normal. Hence, it won't be counted as this current density fully. Now, what then do? We decompose this. We resolve this area element, this area vector, into two components. One along J, that means imagine this normal is resolved into two components. One along J and another along perpendicular to J, and that is this way. Since we have taken J as horizontal, this will be, and this is parallel component of normal, this is perpendicular component of normal. Now you see, if you have area like this, then this N denotes its orientation. This normal denotes. And if you have now normal like this, how do you think should the area be oriented? Definitely like this, so that this must be normal to it. But if you have normal like this, then how should area be this directly oriented? It should be like this. And if you have normal like this, how it should be? It should be like this, horizontal. So we can, what we do here is that we will resolve our area element into two elements. One is this. Now I will show those two. One horizontal, that means this will be one component of this. This is normal and parallel, and another will be this perpendicular. Now this will not contribute to flux current density, because current density will be parallel to it. This will, because current density, this will pulley only the perpendicular component counts of area counts. You see it is perpendicular to this normal. That is the area that I am mentioning here. When I write dq by dt, J is equal to dis divided by this, I mean only this. This will contribute to the current density, not the whole area. So we have actually in dot product, we have two choices. We can take dot product as A B cos theta. That means this is simple product of one vector with component of another vector in the direction of the first. Or you can have A cos theta into B, component of the first vector in the direction of the second into that. So you have choices here. You can take between J dot A, you can take component of J in the direction of A into a full A, or you can take full J but only with component of A in the direction of J. And now I hope you understand these things. Now with this thing, let us now go and write this equation as J is equal to minus, sorry, not minus, J is equal to di, as this is current. By definition of current, you know that is dq by dt divided by dA perpendicular. Now do one more thing, that is dq by dt into dl. I will show you what dl is, divided by dA perpendicular into dl. What is this dl? This dl is, for example, suppose you take an area element like this area element through which current flows, and this flow begins here, and in dt time it crosses this. Taking this thing as soon as it is infinitely small, this time interval, so we can think of this as a cube, or sorry, half a cuboid or a cube. So the question is the distance traveled by this charge dq from this to this is this dl. This dl is the distance traveled in dt time. We can think of this as cylinder as well. It will be better. Now dt. Now you know we can do one thing with this equation. We can rearrange it and write it as dq into dl by dt divided by dA perpendicular into this, that is volume. Now this is volume, area of cross section into dl, that is volume. Now we can write here volume, this volume element from this to this. Now as you can see we have dq into dl by dt. Now dl by dt, dl is distance traveled per unit time. Who travels this distance? This charge dq. Therefore, it is velocity of the charge divided by dv. But what is dq by dt? dq by dt is charge density, volume charge density into v, velocity. And this is, my dear, relation between current density and velocity. We will need this. One more thing. We can write this law of conservation of charge here as minus dq by dt, rate of decrease of charge within that volume element, is equal to. Now, as you saw, that was equal. We found it was equal to dq. It was equal to current, but current itself is equal to. You can write it here. Current. This is di. Current is equal to this into this, and this into this instead of this into this. We can, or yes, exactly. We can write j dA perpendicular, or we can write the same as minus dq by dt is equal to j dot dA, full dA. As I told you, this and this is the same. Now, or therefore we can write dq by dt is equal to minus j dot dA. That is the law of conservation of charge locally. We say that local conservation of charge, where we are not speaking of the whole universe at one time. We are speaking about one small part of the universe at a time. Global and local viewpoints are very important in physics. An example will tell you how important they are. If you have two charges Q1, Q2, and we know that this Q1 will exert a force on Q2, Coulombic force on Q2. This is the force. There are two ways of looking at force F. One way is that we can think that the force is directly coming from Q1. It is coming from Q1 and acting on Q2. Coming from far away distance and acting on this. We call that global view. And in that global view, what we assume? We assume that it doesn't take any time in reaching from this point to this point. It reaches instantaneously. Now, there is another view. The force acting on this charge does not come from this. Rather, it comes from the electric field. Here, there is an electric field, and this force comes from that electric field. Where the charge is, there is an electric field. Which electric field? Generated by this. And that electric field is there, whether Q2 is there or not. That means it is not must for Q2 be there, only then there will be electric field here. The situation is this, that Q1, the moment you place Q1 here, it creates an electric field all around itself, irrespective of whether you bring Q2 or any other charge. It is there. It is as if you have, suppose, a blower, an electric blower switched on in a room, then the temperature at every point of the room will increase. It will be hot. Whether or not you take a thermometer, or whether or not you take a person there who would feel it. So it is therefore the force acting on Q2 comes from the same place where it is. We call this local view. This is local view. So local view. Experimentation has favored local view more than global view. Anyhow, we now have dq. So we have seen we have minus dq by dt minus dq by dt equal to j dot dA. Therefore, dq by dt is equal to minus j dot dA. Now, this gives current through only the small patch of area dA. That is not the whole surface. For a whole surface, you will have to integrate. You will have to integrate it over the whole surface, and replace this charge by total charge enclosed within the surface. This can be done by writing d by dt q charge enclosed within the surface rho dv integral volume integral of that. Rho by rho is the volume charge density into volume integral of that is equal to minus integral s closed integral s j dot dA. Therefore, we can write it as d rho by dt dv is equal to minus integral s. We can use this Gauss's theorem here, and we will write volume, convert this into volume integral by converting j into its divergence del dot j into dv. Okay, leave it as such. Now, equating the two sides, therefore we get d rho by dt is equal to minus del dot j. This is continuity equation. Now, turning to Poynting theorem, we have a region. Suppose we have a particular region of space that has electric and magnetic fields within it. There are electric fields within that space. There are magnetic fields within that space. The sources of these electric and magnetic fields, they need not concern us right now, but one can think of charges, nearby charges, local charges or charges far away, and current distributions which produce these. Or an alternative way of thinking about them is these are electric and magnetic fields of an electromagnetic wave that is passing through this region of space, and while passing through this region of space, the space remains filled at any instant, filled with electromagnetic, at least at any instant means at least for those instants for which we discuss it now, that it fills this space with its electric and magnetic fields. Okay. Now, electric and magnetic fields are places where energy is stored, where there is energy. Electric field or magnetic field both contain energy. Now we want to know how much, and we also want to know one more thing that we want to know is what happens to that energy which is contained within this electromagnet within its volume. Okay. Well, if there is matter there, if there are certain charges, say charge Q here, or there may be, say, currents here. By current, I can mean even moving charges. Those are counted as currents. Now, what will happen? These electric and magnetic fields will exert forces on them. So suppose a charged particle is displaced through a small distance dl by these electric and magnetic fields. How much work is done on that charged particle by electromagnetic field? Work done will be work done by the electric field, that is QE. QE is force dot dl, electric force into displacement plus magnetic force Q V cross B dot dl. Okay. Now, this work done by electric force, this work done by magnetic force. Magnetic Lorentz force. Now, it is an interesting fact that magnetic Lorentz force, does not do any work. Strange it may seem, but we will discuss it after some time, and you will find that this is quite interesting. Now, at this stage, we will avoid it deliberately. Therefore, we can write dW is equal to Q. We can take that common. E dot dl. Even dot d can be taken as common. Dot dl plus V cross B dot dl Rate of doing work is, that's power delivered by the electromagnetic wave to these charges and currents is dw by dt, that is q e plus v cross b dot dl by dt. Therefore, we have dw by dt is equal to, this is velocity, dl by dt is velocity, q into e plus the v cross b dot v, velocity, displacement by time per unit time. Now we can then write it as q e dot v plus v cross b dot v. Obviously this second term is 0 because v cross b is perpendicular to v, so this vector is perpendicular to v, and when you take it is dot product with v, the dot product between two vectors which are perpendicular will give you cos 90 degree, that is 0. So no work is done by Lorentz force. Then we have q e cross e dot v. Okay, we can replace this q by, we can write, instead q we can write rho dv, or in order to avoid confusion with velocity we may write it as volume element. We will be writing volume element now onwards. We will be writing it as d tau. So you have rho d tau volume element into E dot V, that is equal to rho, or we can write it as not rho, we write it as E dot rho V into rho. Now E dot rho V, as we saw, E dot rho V, rho into V, that's current density. This gives us, I'm sorry for this, E dot J into T tau. This is the work done. Therefore, or we can write this is the power delivered by work done per second, that is power delivered by the electromagnetic wave to those charges. While as we can also say that this is the power absorbed by the charges from electromagnetic wave. Quite easy. Now total power delivered will be given by, so we have total power delivered as P is equal to integral of this over the whole volume will be E dot J d tau. Okay. Now we have now E dot J. We will express this. We will write first equation first, and we will express E dot J in exclusively in electric and magnetic terms. That means we will eliminate this J. Now how can we do that? By using product rule from vector calculus that we have already discussed at the beginning of this, and that was del dot A cross B is equal to B dot del cross A plus minus A dot del cross B. Okay, now we want E dot J. Now, where from can we get this E dot J? We have this from, yes, of course, we will have to use one more thing. That is, we will have to use Maxwell's fourth equation. Maxwell's fourth equation, that is del cross B is equal to mu naught J plus mu naught epsilon naught del E by del T. Taking divergence of these two sides with E, so that we get E dot J here. Therefore, E dot del cross B, del cross B. Now del cross B, okay, that will be equal to mu naught del E dot J, okay, plus mu naught epsilon naught D. This is J, we are taking with E, okay, E dot del E by del T, we want this term, so we will have to take this to this side. We'll get mu naught E dot J. This is a term that we require, because you can have a look at this. E dot J is equal to, transfer this to that side, E dot del cross B minus mu naught epsilon naught E dot del E by del T. Now, dividing throughout by mu naught, you have E dot J is equal to 1 by mu naught E dot del cross B minus epsilon naught E dot del E by del T, okay. So we have reached this stage. Now we have this term, this first term on right hand side. We will find its value in terms of product rule that I mentioned at the beginning of this lecture. That is this product rule, del dot A cross B. You may wonder, you may say, well sir, it doesn't have del dot, here it is E dot. Well, you see, if when you write it this side, you will have A, B first, you have B dot del cross A minus A dot del cross B. We will find this term here by realizing that if we treat A as E and B as, instead of B we have B, magnetic field, then this will be del dot E cross B, del dot E cross B is equal to B, that is B dot del cross A del cross E minus A, that is E dot del cross B. You can see now this last term is the term that we are looking for. So we will get its value from there. We simply transpose this to this side and transpose this to that side. Therefore, we will have E dot del cross B is equal to del dot E cross B plus or minus, no plus, sorry, plus B dot del cross E, del cross E. So the sign of the second term on LHS, we have written that wrongly as positive, it is negative. Let us correct that. We write E dot del cross B is equal to B dot del cross E minus, it is minus actually, you can check it yourself, dot E cross B. Now using this value of E dot del cross B in expression for this E dot J that we already derived, we have then, therefore we have E dot J is equal to 1 by mu naught E dot, now we have now E dot del cross B. This is the expression for E dot J that we derived already. We have then E dot del cross B minus epsilon naught E dot del E by del T. Now we can use now let's keep it as it is, E dot del cross. No, this is the value. Is this the value of E dot del cross B? Is that value is this? This is to be substituted in its place here. Now in expression for E dot J, when we do that, we get E dot J 1 by mu naught, and now we have B dot del cross E minus del dot E cross B, and minus, then outside we have minus epsilon naught E dot del E by del T. Next step, we use Faraday's law for del cross E. According to Faraday's law, del cross E is equal to minus dB by dt. Maxwell's third equation, del B by del T. Substituting that in place of this, we get, therefore we get E dot J is equal to 1 by mu naught B dot minus del B by del T, then minus del dot E cross B minus epsilon naught E dot del E by del T. Now next we use a simple result from vector calculus. Suppose we have to differentiate del by del T B square with respect to time. Now we can do it like this. We can write del by del T B square, in place of B square we can write B dot B. Okay, because B dot B is B square. That we can now use U into V rule. Simple this rule from differential calculus. U into V rule. We differentiate B, keep the other B there, other B as such. Now differentiate. Now put the first B there and differentiate this. Since dot product is commutative, hence we can simply write it as twice b dot del b by del t. So in place of del b by del t that we have here, b dot del b by del t, we can write, therefore we can write b dot del b by del t can be expressed as 1 by 2 del by del t b square. Similarly, we can write e dot del e by del t by 1 by 2 del by del t e squared. Using these results in this equation for e dot j, we get e dot j is equal to e dot j is equal to 1 by mu naught minus, this minus we will take outside, so b dot del b by del t minus 1 by mu naught b dot del b by del t, that is 1 by 2 del by del t b square. Then we have minus. If I take this minus as a whole common, then I will have to supply. See, this second term is minus, but taking a minus outside, I will have to write it as plus del dot e cross b del dot e cross b. Then lastly I have this epsilon naught e dot epsilon naught. The next term is epsilon naught minus epsilon naught e dot del e by del t, that is 1 by 2 del e by del e square by del t. Next, what I do, I group these two terms at one place. I write, therefore e dot j is equal to minus 1 by 2, this is common to e square and b square term, minus 1 by 2. Further, del by del t is also common to the two terms. This leaves us with e square epsilon naught e square plus 1 by mu naught b square, or b square by mu naught, and the term, next term left is that is 1 by mu naught. Be careful about this 1 by mu naught. You often simply drop it unknowingly, and that creates problem. Minus 1 by mu naught del dot e cross b. Now the total work done on the charges in the given volume is given by E dot J del tau V, if we denote entire volume V by V is equal to minus 1 by 2. Yes, that one can take this common. We have del by del T, then again volume integral of epsilon naught E square plus B square by mu naught d tau minus again volume integral 1 by mu naught volume integral of del dot E cross B d tau. The last, that means this integral can be converted into surface integral using Gauss's divergence theorem. So we will be having this. First of all, let us write that you have to consider E cross B as one vector. Think of this as a vector, say C, vector C. Now, this then becomes del dot, you have something like this, volume integral of del dot C, and d tau. This is volume element. Now, that is equal to, according to Gauss's theorem, this is equal to, this is divergence of C on one side and flux of C on the other side. Flux of C is C dot dA. Divergence flux, that is the theorem, Gauss's theorem. Now, divergence equal to flux with, of course, with these minor things that you can remember. Now, as usually we do not enclose and put a circle on this. We understand that it is bounded region. Now we have C dot dA. Now instead of C, you have E cross B here. Therefore, you have integral V E dot J d tau is equal to minus 1 by 2. Now you have minus 1 by 2. Yes, 1 by 2 del by del T integral V epsilon naught E square plus B square by mu naught d tau, and then lastly this minus 1 by mu naught minus 1 by mu naught minus 1 by mu naught. Okay, then when you convert it into a surface integral, we have surface integral as del dot, this divergence is to be converted into flux. Flux will be E cross B dot dA. Now the quantity, this quantity, for example, this quantity, most of the students will be familiar with these. These are basically electric field energy and magnetic field energy. That means energy is stored in the form of electric field. In electric field, energy is stored in a magnetic field. We assume that these results that we have already seen in mostly in static case, this result, for example, in electrostatics, for example, is also applicable to current state. And we, if there are students who find it difficult to understand that this is energy per unit volume, electric energy per unit volume, a simple example may convince such students. We cannot go for entire derivation. That will take us time and unnecessarily confuse most of you. So just as a bit of, say, food for your curious mind. That is, suppose we have a parallel plate capacitor with no dielectric. It is distance between plates is D, area of plates is A. Now there is something that takes out positive ions from this plate, and deposits on this. Now this plate will become negatively charged, and that plate will become positively charged. Because of this, the capacitor will be charged. There will be an electric field inside the capacitor. But in order to establish this electric field, you have to charge this capacitor. But for charging, you need work. The agent that charges it has done work. Why? Because when he lifts positive charge from this plate, he has to fight against attraction of these negative charges. And when he deposits that positive charge here, he has to, of course, fight against repulsion of these positive charges. Work is being done both in extracting charge from this and depositing here. This work is stored in the field. We believe at least it is stored in field, and how much this work is, that can be easily determined. This work is equal to, that has, actually we have a formula for energy stored on a capacitor, that is energy we denote by capital U 1 by 2 CV square. This is expression for energy stored in a capacitor, that is equal to 1 by 2 C. Capacitance of a parallel plate capacitor is epsilon naught A by D, and potential difference between these two, this voltage or potential difference, that potential difference is equal to work done per unit charge. Work done per unit charge is E into D. How? Work is equal to force into displacement. Now this is force per unit charge. F is total force, but we are speaking about force per unit charge, that is E. So this is the work done on a unit charge in taking it from this place to this place, square, that is 1 by 2 epsilon naught A by D into E square D square. D and 1D goes, we are left with A, area of cross section, into D, distance between them, that is volume of the capacitor. Therefore, taking this volume on this side, A, D will be equal to epsilon naught E square 1 by 2 divided by 2, 1 by 2 epsilon naught E square. So this is energy per unit volume. We denote it by small u, electric energy, UE. That is electric energy. Energy stored per unit volume of this field. Okay. Now, similarly, you can think of this other term. So we have now E dot J, coming back to our topic, that is E dot J volume integral delta is equal to, minus 1 by 2. 1 by 2 will now have to be absorbed here, and here both are required there. So we can write 1 by del t minus del by del t minus del by del t, and inside we have to write 1 by 2, that is UE electrical energy, now plus UB magnetic energy, and then we have lastly this minus 1 by mu naught and surface integral of E cross B dA, E cross B dA. Now let us look at this last integral. It is interesting. Now what this integral means, you can see it. This whole thing, these two they constitute a vector. This is a vector. E cross B is a vector. Of course, looking at E cross B does not mean these are two things. When you take their cross product, that is another vector. That is neither E nor B. It is something different. Something like 3 into 4. It is neither 3 nor 4. It is 12. So E cross B is something 12. Some different vector. Now that vector, if you write for a moment, if you write C for that, what is this C dot dA? We compare it with E dot dA, electric flux. So it is, we can say, on analog space, on lines, we can say E cross B dot dA is flux of, this is flux of E, a vector, namely E cross B. So this is flux. Something is going through the surface. This is, when you take its integral, you are calculating actually total flux. So something is going through the surface. Now, the question is, what is it that is going through the surface? Now, let us see. This whole thing must be energy per second. Because this is energy per second. So this too must be energy per second. Now, if this is whole, because all terms must be dimensionally, must have same dimensions. So based on that, we can write it here. This is dimensionally 1 by mu naught, or this might divided by, you have no, we must have it along with this mu naught. You have we can absorb this mu naught here, we can write it here. So we can write 1 by mu naught E cross B is some sort of energy per second multiplied by area. Now multiplied dotted with area. Now particularly for simple way of convincing you, I will consider this vector and dA parallel. This vector and dA parallel. If they are parallel, then E cross B dot dA can be replaced by E cross B dA. If now I divide it by dA, I now have energy per second per unit area. By dividing area, I have energy per second per unit area. So E cross B divided by, of course, 1 by mu naught is energy per second per unit area. This energy per second per unit area, energy per second, if you take energy per second, that is called power. In physics, it is technically called power. Now per second per unit area, power per unit area is basically some sort of intensity, power area, power per unit area. Something you have heard of solar constant, something like intensity of light. Now this is some sort of an intensity. What intensity it is? Energy intensity. Which energy intensity that crosses this closed surface in perpendicular direction because of dot product. That means you had that volume element, say V, which was bounded by surface S. There was an electromagnetic field there, and energy and this say there was an electromagnetic wave. This electromagnetic coming wave has some energy. That energy is represented by this term, this much. Electric energy and magnetic energy. In the form of, it has electric energy plus magnetic energy. In the form of fields, electric field and magnetic field. And when it goes through this matter there inside the volume, that absorbs, it does work on that matter, on charges here, on currents here, and there will lose its energy to them. The energy that it loses is given by this. This is the work done by this on those charges. Now that is it. Plus, then what is left? The amount that is left crosses through this surface. In all directions, of course, in all possible directions, cross through this surface. This amount which crosses through this surface is represented by this equation. So this means that this equation is a statement of law of conservation of energy. It is called Poynting Theorem. We can write it more simply as dw by dt is equal to minus del by del t integral v u del tau minus integral s dot dA, where s is called Poynting vector. So this is another way one can look at Poynting theorem. We will talk more about Poynting theorem in our subsequent lectures, but for the present this is enough, and we actually finish this lecture right at this stage. Thank you.